Hi everyone. So last week's lecture we were focused on the Fourier transform and the math behind it. And in the ending of last week's lecture, we saw that an application of the Fourier transform is regards to obtaining a magnitude and frequency plot, which is referred to as the Bode plot. So today's lecture is actually how do we go about constructing a Bode plot with respect to its magnitude and phase plots. So if we consider this following transfer function here in the Laplace domain, it is similar to that of a second order transfer function that we have seen in previous lectures. Now, questions arise that how do we plot or how do we obtain the magnitude versus the frequency and the phase versus the frequency of our example equation here, which is also referred to as our example system. So we know that the relationship between the S domain and J omega domain is if we just substitute S is equal to J omega, and such that we can do the substitution and we can get a represented equation form here in J omega. But the question is, how do we proceed from here in doing this? So we could do substitution, which is a very long way to evaluate the frequency response for values of omega, or we can actually do asymptotic Bode plots, which was developed by Mr. Henry Bode, who worked in Bell Labs. And this Bode plot basically gives us two plots, which are the gain plot or the magnitude plot, and a phase plot or the angle plot. So the following examples that are coming up are basically the rules that you need to know for any type of Bode plot that we're going to be doing. And once we know all the rules for this, when we do Bode plots 2 and Bode plots 3, you can actually see that all these rules come into effect, especially when we need to superimpose Bode plots on top of each other. So it's very important that you need to pay attention and remember the following examples that are coming up in this lecture. So our first example is if our Laplace function h of s here is equal to some constant. If we try to find the magnitude versus frequency here, and this is given as the square root of the real squared plus imaginary squared components, what we will get here is that it's basically going to be a constant. And if we try to find the phase of it here, we know that depending on the sign of the constant, it's going to be a different angle phase. So the angle of phase is normally given as the tan inverse of the value that we are trying to find for. So in short, if k goes positive, we're going to be starting at the 0 degrees line, but if k is negative, we'll be going at the minus 180 degree line. So in general, for the magnitude plot, we tend to represent this in decibels. And the equation for this mapping from a constant or any real and imaginary component or imaginary number that we may be given is 20 log 10 of whatever that equation is. And because we're using a log equation here, that means our x-axis needs to be in a logarithmic scale. But because basically if we try to plot for a very large range of frequencies, which is represented on a log scale, it's going to run out pretty fast if we decide to draw this on paper. So a generic scale looks like this, where our y-axis is represented in magnitude decibels, and our x-axis here is represented in frequency radians. Now, it is important to understand that our gradients, our graduations here, is that the magnitude versus decibel follows a somewhat linear scale, meaning that we start from 0 here and we go all the way up to 1, but our x-axis here, which is our frequency scale, follows a logarithmic fashion, meaning that in between 10 to the power 0 and 10 to the power 1, these intervals here would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 accordingly, but from 10 to the 1 to 10 to the 2, this now becomes 10, 20, 30, 40, 50, and so forth. And then here will become 100, 200, 300, and so forth as we keep on going along. Our phase plot also follows the same way, in such that the angle here is in between positive 180 degrees and negative 180 degrees. And our frequency axis here, or x-axis, also follows the same thing as if it was for the magnitude plot. Now, in drawing out example 1, we knew that 20 log of a constant will just basically give us a representative constant in log scale. So it would just look like a horizontal straight line here for our magnitude plot for whatever 20 log k is. And our phase plot here, well, as we know, is if k is positive, it'll be at the 0 degree line, and if k is negative, it'll be at the negative 180 degree line. Now, our second example here is that if we introduce an s component here, but in this case the s component is at the denominator. If we try to find the magnitude versus frequency of this, we know basically if we substitute s equal to j omega, we will get the following equation here, highlighted in green. And as of such, 1 on j, if we watch this on real versus imaginary axis, is that 1 on j has an angle of minus 90 degrees. If you remember that the real axis being the x-axis and the imaginary axis being the y-axis, be it for our real versus imaginary plot for any imaginary number, you will realize that if we rationalize 1 on j, we will basically get minus j on the numerator. Rationalizing means that we multiply by j on the numerator and j on the denominator. And minus j on the imaginary plot is literally on the negative y-axis. And we take the angle going clockwise from the positive real axis going all around clockwise. So minus j will be at the, no, we take the angle, going anti-clockwise, meaning that we start from the positive real axis and then we go to the positive y-axis and we keep on going as of such. So that will start from the 0 degree line to the positive 90 degree line, and then we go to the positive 180 degree and then the positive 270 degree. And because it wraps around 360 degrees, this in turn means that we can say 270 degrees is equivalent to minus 90 degrees. Now, in trying to find the magnitude here for this equation, because the omega component is on the denominator, it comes like if we do 20 log of k, which is the numerator, but the denominator is represented by a minus sign connecting that 20 log of omega. Now, 20 log of k we know is a constant, but what happens when we have 20 log of omega? What happens here is that we get a linear slope where we draw each of the individual components here. So we draw here for 20 log of k, knowing that at this point here, when omega is 1, the 20 log k is unaffected. But for 20 log k on omega, we know such that when omega is 1, we get a certain value here. But then when omega is equal to omega, it comes like this is 20 log of 1, so we get an next value here. And as omega keeps on increasing, we also get an next value here, resulting in this linear behavior as we just see here. The end result would be such that we need to find out what is the gradient of this linear behavior. So let's consider some omega values in order to find the gradient. So we know when omega is equal to 1, our resultant magnitude equation would be 20 log of k. And then when omega is equal to 10, our resultant large magnitude equation would be 20 log k minus 20. And if we take a difference of these two to see what is the change of the magnitude in between these 2 points, we basically are going to get minus 20 decibels. And because this change happened across omega 10 to omega 1, this is what we refer to as a tenfold change, which is a decade. And we just now saw from the previous graph that the behavior of this was linear. So our slope therefore has a minus 20 decibel per decade gradient accordingly. So this actually is our resultant graph for example 2 here, indicating that the slope will have a constant gradient of minus 20 decibels per decade. Our resultant phase graph for this would be such that we'll have a constant phase of minus 90 degrees. Now if we consider the S component here being on the numerator, it is the opposite of that of the S component being on the denominator. So as of such, since it's now the opposite, that means that our phase here will be a constant of positive 90 degrees, and our resultant magnitude equation, instead of it being minus, it now has plus. So I just answered the question what was the phase versus frequency, but instead of this slope now being such that it had a minus 20 decibel per decade gradient, it is the opposite here because the S component is on the numerator. So as of such, instead of being minus 20 decibels per decade, we now have a positive gradient, indicating that this is positive 20 decibels per decade. And of course, the constant phase of 90 degrees can be seen here graphically. Now for example 4, what we observe here is that what happens if we now have polynomial powers of S. And how would this change our plots accordingly with respect to this? So the magnitude versus frequency now means that we introduce an n multiplicative component into our magnitude versus frequency, as well as our phase versus frequency. So our phase equation here now means that we need to indicate that we have a minus n component, but it is going to be affected such that it is in intervals of 90 degrees. And because the S component is on the denominator, this is how we have this minus 90 degrees accordingly. Similarly, because we now have this n component here for our magnitude equation, this means that this n component is now in front of the 20 log omega, as we just now saw when n was equal to 1 in example 2. So as of such, this means that our gradient now is represented in 20 n decibels per decade, and because the S component is on the denominator, this means it is now going to be minus 20 n decibels per decade. So what happens here is because of these powers of n affecting our S component here, this now means that our gradient is affected accordingly by a multiplicative factor, and our phase here is affected accordingly by a multiplicative factor as well. Our gradient here is given as minus 20 n decibels per decade, and our phase here is given at minus n 90 degrees. Whatever the value of n is indicating the highest power of S, that will determine our resultant graphs. So graphically what this looks like is that we can see if n equal to 1, we're going to have a minus 20 decibel per decade slope, but as n increases, for n equal 2, this is going to be minus 40, and then for n equal 3, this is going to be minus 60 decibels per decade. For our phase plots, what this means now is that for n equal 1, if it was k on S, as we saw in example 2, it was minus 90 degrees, but as n increases in value, we now go, when n is equal to 2, minus 180, and n equal 3, minus 270, and so forth, for increasing values of n. Example 5 is basically the opposite of example 4, because now the S component is on the numerator. So instead of it being minus n 90 degrees for our phase, it's now positive n 90 degrees. And our resultant magnitude equation means instead of it being minus 20 n decibels per decade, it is now positive n 20 decibels per decade. So our resultant graphs as seen here is basically the opposite from what we observed with respect to example 4. So now we have 20 decibels per decade here, 40 decibels per decade here, and 60 decibels per decade here. And accordingly, our phase plots mean that we have positive 90 degrees, positive 180 degrees, and positive 270 degrees for n equal 1, 2, and 3 accordingly. Now what happens if we introduce a pole, meaning S factor, on our denominator? So the behavior of the graph will change accordingly, but it will be similar to that what we observed in previous examples. So if we substitute S equal to j omega into the equation, and then we do something we refer to as we standardize the equation, where we make our pole here 1, and the rest of the equation is affected accordingly. It comes like if we divide the numerator and denominator by p in this equation, and we get the resultant equation looking like this here. And plotting the straight line approximation for this, the component we pay attention to is this omega on p component here for imaginary component. And we want to observe for 3 conditions when p is much less than omega, p is equal to omega, and p equal being more than omega, or much greater than omega, how actually do we obtain the plot accordingly for each one of these conditions? So in obtaining the magnitude versus frequency graph here, if omega on p is much less than 1, or omega is basically much less than p, we can basically say that this j omega on p term here will go to 0 accordingly. Because if this is omega is much less than p, that means that it comes like this is a very small number on top here being divided by a very large number here. So that basically goes to 0. And accordingly, this means that we will get a result of 1, and if we take 20 log of 1, the result here is going to be 0. If in the event where omega is much greater than p, meaning omega tends towards infinity, the math here indicates that we will end up getting minus 20 log of omega as omega tends towards infinity. And we saw from our previous examples that this would end up resulting into a minus 20 decibel per decade slope. Think back to like our example 2 and example 3 as to why we obtain this minus 20 decibel per decade slope accordingly. So what happens if we plot these 2 conditions is that the horizontal graph looks like this, where for everything before the pole value we'll have a constant 0 decibel per decade line here, but everything after the pole value we're going to have a constant minus 20 decibel per decade line here. The point at which omega is equal to p here is what we refer to as our corner frequency, or break frequency, or cutoff frequency. You may be familiar with the term cutoff frequency from when you're doing your amplifier designs. So what happens at the corner frequency is that if we try to find the magnitude for this accordingly, and we do the math behind it, which is given by this equation here, we can see that the result will end up being a minus 3 decibel result accordingly. And this minus 3 decibel result sounds very familiar, especially when you came to the realm of electronics. So when we were designing for a cutoff frequency or a corner frequency in particular, we knew that we need to indicate that we had to take into consideration a minus 3 decibel per decade, a minus 3 decibel cutoff point for any amplifier or filter design that we were doing. The maths here indicate that this is why we accommodate for this, because of when the pole value is equal to the omega value. So if we actually plot this out accordingly, this means, given by our red line here, as we can see, this is what the actual true graph will look like. But however, for the purpose of this course, we are doing straight line approximation, so we don't actually need to plot this dotted red line here to indicate this minus 3 decibel change. What we just need to do is plot everything for omega much less than p and omega much greater than p accordingly. If we pay attention to the phase versus frequency, we also pay attention to those three conditions as well. So for omega much less than p, what will happen here is that our resultant angle here will go to 0. For omega much greater than p, our resultant angle will end up going towards infinity, meaning that we'll have a result of minus 90 degrees. And at our corner of cutoff frequency, when omega is equal to p, we can see that the resultant angle here will end up being 1. And as of such, tan inverse of 1 means it's 45 degrees, and the minus sign in front of it means that it goes to minus 45 degrees. Now, what we consider here is that how do we plot a straight line approximation for this on our pole, or sorry, on our phase plot? So what happens here is that we only consider what happens at omega much less than p and omega much greater than p. But in this case, for the phase plot, we now have to consider what happens at omega equals p. So for omega much less than p, we know that the angle the resultant phase would be that it would be at 0 degrees. At omega equal p, we represent this change here that is supposed to be a nice S curve, given by our dotted line here, as a vertical straight line accordingly, since we're doing straight line approximation points. And we know for the omega much greater than p, this is going to be minus 90 degrees. So this is actually how we represent our phase plot accordingly. For a single zero transfer function, as given here in the example 7, is basically the opposite of what we saw in example 6. So we can do basically our math again, where we substitute s equal to j omega, and we rationalize it accordingly, such that we have our j term here being such as omega divided by p. And then we can actually plot our straight line approximation accordingly as well, with respect to this. So if we think our magnitude versus frequency here, and we consider our three conditions from before, for where omega divided by p is going to be much less than 1, where omega is much less than p. We're basically going to get that at this point it's going to be 20 log 1 again, which is going to be 0. But if we consider omega much greater than p, instead of the result being such that there was a negative sign here for example 6, there's no positive sign here, because all the components that we're dealing with for the magnitude is now in the numerator accordingly. So that's why we have this positive sign here when we try to find our magnitude of a resultant graph. So that results in positive 20 log omega as omega tends towards infinity, resulting in a positive 20 decibel per decade slope. And what happens is that our resultant graph now looks like this. So everything before the everything before the 0 is at 0 decibels per decade constantly, and everything after the 0 means that it's going to be positive 20 decibel per decade. If we pay attention to the phase accordingly, this means instead of it being that is a negative tan inverse, it's now a positive tan inverse because of all the components being on the numerator. So that means for everything less than the 0 value, we're going to be at 0 degrees. Anything much greater than the 0 value, we're going to be at positive 90 degrees. And everything equal to the pole value, we will have that 45 degree change that we saw accordingly as well. So our resultant graph is basically the opposite of the phase graph that we saw in example 6, where such that at 0 degrees, for everything less than the 0 value, we'll be at a constant phase of 0 degrees. Everything at the 0 value, we're going to have that 45 degree change seen by this red line here, but because we're doing straight line approximations, it's going to just be a vertical line. And for everything much greater than the 0 value, we're going to be at a positive 90 degrees. Please ignore the signs here, that's basically an error in the slides. So this is actually supposed to be positive 45 degrees and positive 90 degrees. Alright, so that brings us at the end of today's lecture. Hopefully that this method that we're using here to deliver lectures online is somewhat effective. If there are any questions or anything that needs to be resolved, please comment down in the box below. and we shall respond to you accordingly and give you feedback as well. All right, that's it for today's lecture. Good night.